Okay, in the last lecture, we seen that one theorem, the Galois group of a polynomial over the field of f, okay, with characteristic 0 is isomorphic to group of permutation of its root. Okay, so look at here. Let f of x be a polynomial over the field f with characteristic 0, and k be the splitting field of f of x over the field f. And what is given to us? Then k is normal extension of f, okay, by theorem. So the Galois group GKF of f of x is a finite group, okay, and the degree of k over n is equal to n by the corollary. The degree of k over f is equal to order of GKF if k is normal extension of f. And assume sigma 1, sigma 2 up to sigma n be the n distinct automorphisms of GKF. Now suppose f of x has only m distinct roots in k. Okay, this is the field K. This is the set A, which contain alpha 1, alpha 2, all the m distinct roots in S. Okay, set of all the roots of f of x. So it is possible that f of x may have multiple roots, but the set S contain only distinct roots. So what is this? S is equal to alpha 1, alpha 2, up to so on, alpha m with the set of m distinct roots of f of x in capital K. Okay, now what is the set P? P is the set of all those permutations on S which change only those elements of S which are not in F. That is the set of all those permutations which leaves every element of F is fixed. Okay, on this one. If the alpha belongs to this section, then that sigma, that permutation, the element belongs to the set P fixed to that element. Okay, so P is the what set of all those permutations on S which change only those elements of S which are not in F. That is, which leaves every element of capital F is fixed. Okay. Now, if G1 and G2 are the two elements of P, then G1 into G2 composition. G1 composition G2 is also with the element of P. Okay, which leaves the element of F is fixed. Hence, P is the closest with respect to product of permutation, and we showed that P is the subgroup of the group of all the permutations on yes. Now, we have to show that this GKF is isomorphic to set P. Okay, what is P? Set of all those permutations on S which leaves every element of F is fixed. So yes, if sigma belongs to GKF, okay, now sigma belongs to GKF means what? Sigma is the automorphism of K which leaves every element of F is fixed. And sigma star with the restriction of sigma to yes. Okay, that is sigma star is equal to sigma for all alpha belongs to S. So this sigma star and sigma both behave like same on the set of finite elements, that is set yes. So if alpha is the root of f of x, then we know that sigma of alpha is also root of f of x. Why? By this theorem. Root maps to root if E is the extension of field f and f of x belongs to the capital of x and alpha, and phi is an automorphism of E, then root maps onto root. Okay, so if alpha is the root, then sigma of alpha is also root of f of x in K. So therefore, for all alpha belongs to yes, sigma star is equal to sigma. Okay, that means sigma star is what? Restriction of sigma. So here sigma is automorphism, that is 1 1 and on 2. Hence sigma star is also 1 1, and every 1 1 function on the finite set is onto. Hence sigma star is onto and 1 1 also. Hence sigma star is what? Permutation on S which leaves every element of F is fixed. Okay. So here it follows that sigma star is also leaves the every element of F is fixed. Now the sigma star is what? 1 1 on 2. That means it is permutation. Hence sigma star belongs to capital P by the definition of P. Okay, and sigma of alpha is equal to alpha for all alpha belongs to F. Okay, any doubt up to here? Now we have to show that there is a mapping psi between GKF to P, and we have to show that that psi is 1 1 onto and it results the operation. Okay, हे उद्योग का करायचं सगळं की आपल्याला आता मॅपिंग डिफाइन करता येईल. Look at here. Let psi is psi be the mapping. Psi be the mapping from G, K, F to the set P. Okay, defined as. Wait a minute. Wait a minute. Let psi be the mapping from GKF to P. Let psi be the mapping from GKF to P. Psi of GKF. Psi is the mapping from GKF to P defined as what? Sigma. Psi of sigma is equal to sigma star, where this sigma belongs to GKF. Okay, write down this one. Wait a minute. What is psi? Psi is the mapping from GKF to P. Okay. Defined as psi of sigma is equal to sigma star, and this sigma star is nothing but restriction of sigma. Okay, for all sigma belongs to domain, that is G, K, F. Now, in the first step, if you have to show this isomorphism, in the first step, you have to prove that this psi is 1, 1. Okay, what is the procedure to show the oneness? Let sigma 1 and sigma 2, these are the two elements belongs to GKF, the arbitrary element. Okay, arbitrary. And let the images are equal. Psi of sigma 1 is equal to psi of sigma 2. Okay, what is the definition of psi? Sigma 1 star is equal to sigma 2 star. Okay, sigma 1 star of alpha is equal to sigma 2 star of alpha. Okay, which is equal to sigma 2 star of alpha. Okay, alpha star, sigma star is the mapping on S now. So this is for all alpha belongs to capital yes. Okay, so this implies that sigma 1 and sigma 1 star both are equal on set yes. So this is sigma 1 of alpha, which is equal to sigma 2 of alpha for all alpha belongs to yes. What is the reason? Sigma star, sigma 1 star and sigma 2 star are restriction of sigma 1 and sigma 2 on this set yes. Okay, but we have to show that sigma 1 is equal to sigma 2 on whole field K. Okay, this is the field K, this is F, and this one is yes. Okay, here we showed that sigma 1 and sigma 2 are equal on the this set. Okay, but we have to show that whole the field K. Okay, but what is K? K is nothing but splitting field of polynomial. That means if you join the all the roots to the base field, we get the bigger field K. Okay, so on this is alpha m. But K is equal to what? F of alpha 1, alpha 2 up to so on alpha m. Okay, K be the splitting field of f of x belongs to capital F of x. Since what is the reason for this step? Since K is splitting field of f of x and alpha 1, alpha 2 up to so on alpha m are roots of f of x in K. Any doubt up to here? Okay, now therefore, now
No,
we have
sir.
to show that this alpha 1 is equal to sigma of alpha, sigma 1 is equal to sigma 2 on whole set, whole the field K. Okay, whole field K. Now, Therefore, look at here. If k is equal to what? F of alpha 1 up to so on alpha n. Therefore, what is the meaning of this one? Therefore, each element of capital K, okay, is obtainable is obtainable as the result of finite number of operation. Okay, therefore each element of K is obtainable as the result of finite number of operations of addition, subtraction, okay, multiplication, and division, okay, by non-zero elements, non-zero elements performed on the elements of F. Is it correct? Elements of F and on
Yes,
alpha
sir.
1, alpha 2, up to so on alpha. Okay. Now look at this statement, the meaning of this statement. What is K? K is equal to F of alpha 1, alpha 2, up to so on alpha m. Okay. So every element of A belongs to K. We can write in the form of elements of F and elements of this one. Okay, this statement clear. So therefore, each element of K is obtainable as the result of finite number of operation of addition, subtraction, multiplication, division by non-zero elements performed on the elements of F and on alpha 1, alpha 2, to on alpha m. Okay, but sigma 1 and sigma 2 are automorphism of capital K. Each of them, each of them leaves every element of capital F fixed. Okay, and each of them maps every element of S identically. Okay, each of them maps every element of S, which is equal to what? Alpha 1, alpha 2, up to so on alpha m identically. Why identically? Because sigma maps roots to roots. Na? So this is identical. Okay, that is what is the meaning of this one? Sigma 1 of alpha is equal to sigma 2 of alpha for all alpha belongs to capital S. Okay, so therefore, this sigma 1 of alpha, sorry, sigma 1 of beta, okay, take the beta from the K now, is equal to sigma 2 of beta for all beta belongs to capital K. Hence, sigma 1 is equal to sigma 2 on K. This implies psi is 1, 1. Is it correct? Any doubt up to here? Okay,
No, sir.
look at this one. The next one. Now we have to prove that the psi is 1, 2. Okay, wait. Second. To prove that psi is on 2. Okay, now for the continuous, take the let G be any element. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, any element from the codomain. Okay, what is codomain of capital P? Then G is what? G is a permutation. Permutation on set yes, leaving those elements of S are fixed, leaving those elements of this S fixed, which are in which are in capital F. Is it correct? Now suppose
Yes.
there exists an automorphism. There exists an automorphism. Okay, sigma belongs to sigma of K. Sorry, there exists an automorphism sigma of capital K, which leaves every element of F is fixed. Every element of capital F fixed, and which maps the element of yes in the same manner. In the same manner as G maps. Okay, this is the field K. This is F. This one is yes. Okay. What is P? The set of all permutations on this set yes. Set of all those permutations on yes, which leaves every element of F is fixed. Okay. So if G belongs to P, what is the meaning of this one? G is the permutation on this set yes, which leaves every element of F is fixed. Okay. Now check the sigma belongs to what? GKF. Okay. If the sigma belongs to GKF means what? Every element of F is also fixed. This sigma, every element of F is fixed by the definition of GKF. आणि हा G बाकीच्या एलिमेंटला कसा मॅप होतोय तसाच हा सिग्मा पण मॅप होतोय. ओके, असा फंक्शन घेतलाय पण असा सिग्मा घेतलाय. टेक सिग्मा बिलॉंग ऑफ के. Okay, the automorphism sigma of K, which maps every element of S is the same manner as G maps. हा G कसा मॅप करतोय तसाच हा सिग्मा मॅप करणार आपण ऑटोमॉर्फिझम घेतला. ओके. There exists an automorphism sigma of K, which leaves every element of F is fixed. That is, sigma belongs to GKF, and which maps the element of F is in the same manner as G maps. Okay, so hence the sigma is completely determined. Okay, the sigma is completely determined. ह्याचं एक्सप्लेनेशन नंतर अजून सांगेन नंतर एक थेरम संपल्यानंतर. ओके, हा सिग्मा असाच काय होतो. There exists a sigma such that psi of sigma is equal to P. Okay, so here hence sigma is completely determined. So this sigma belongs to what? GKF. No? Wait, this sigma belongs to GKF. GKF, and also the restriction of sigma. Also the restriction of sigma 2 set yes will be what? 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. हा सिग्मा रिस्ट्रिक्ट होईल कोणावर एस वर. This sigma is restriction of sigma to S will be now G. Okay, so G is the what? Is the function one function on the set of yes finite set yes. म्हणजे काय हा तुमचा सिग्मा येस वर कसा अप्लाय होतोय जी सारखा अप्लाय जी सारखा मॅप होतोय. ओके, so thus for any G belongs to P, for any capital small G belongs to capital P, there exists sigma belongs to G K F such that this psi of sigma is equal to G. So and hence psi is on 2. Is it clear? Okay. Any doubt up to here? Okay. In the third step, we have to prove that
No, sir.
theta preserves the composition. To prove that, sorry, theta not psi. Psi preserves the composition. Okay, now let sigma 1 and sigma 2 belongs to G, K, F, be any arbitrary element. Okay, then psi of sigma 1, sigma 2. By the definition of psi, we have sigma 1 into sigma 2 star. Okay, the restriction of sigma 1, sigma 2 to yes. Okay, what is sigma 1 into sigma 2 star? This is the restriction of sigma 1, sigma 2, sigma 1 into sigma 2, okay, to yes. But for all alpha belongs to yes, we have. But for alpha belongs to yes, we have sigma 1 into sigma star. For all alpha belongs to the set yes, we have. This is sigma 1 into sigma 2 star of alpha. If you apply this function to alpha, what we have? Sigma 1 into sigma 2. Okay, this function is equivalent to yes, no? So this one is alpha by definition of sigma star. Okay, that is sigma star is the restriction of sigma on the set yes. So this is equal to what? What is sigma 1, sigma 2? These are the automorphism. So this preserves the operation. This is sigma 1 into sigma 2 of alpha. Okay, so which is equal to this is sigma 1. Sigma 2 is nothing but sigma 2 star of alpha. Okay, so which is equal to what is sigma 1? Sigma 1 star. Sigma 2, this is star of alpha. Okay, on S, we have sigma 2 is equal to sigma 2 star. Now this one, assume this one is element. And now what is sigma 1? Sigma 1 is equal to sigma 1 star on yes. So this is equal to sigma 1 star into sigma 2 star of alpha. Okay, so this implies sigma 1 into sigma 2 star is equal to sigma 1 star into sigma 2 star. Hence, we get psi of sigma 1 sigma 2 is equal to sigma 1 star into sigma 2 star, which is equal to psi of sigma 1 into psi of sigma 2. Hence, psi is an isomorphism from GKF to P. This implies GKF is isomorphic to set P, and P contains set of those automorphisms. Sorry, set of those permutation on S. What is S? Roots of f of x. Okay, distinct root of f of x. Permutations of permutation on roots of that function polynomial f of x. Set of those permutations on S which leaves every element of f is fixed. And what is GK? Set of those automorphisms of K which leaves every element of f is fixed. Okay, so here the GKF is isomorphic to permutation group. Okay, any doubt? Okay.
No, sir.
हा तुमचा सिग्मा इज इक्वल टू जी कसा आला इथे? Look at it. What is here? What is sigma is ontoness in the ontoness. G is the permutation on S which leaves every element of F is fixed. And for this G, there exists an automorphism sigma of K. Okay, that is this sigma belongs to GK such that we show that here psi of sigma is equal to G. असा कसा होतो? Now look at this. This is the field K. This is F, and this one is yes. Now, if G belongs to set P, so this implies G is permutation on set yes. Okay. Now, our aim is to say this sigma belongs to GKF. Okay, the automorphism of K. Automorphism on K, there exists such that this psi of sigma is equal to G. Okay, हा आपल्याला प्रूव्ह करायचं. हा कसा कसा okay. Now, then this sigma belongs to what? GK. Okay, if we have to show that this one psi of sigma is equal to G, so this sigma possesses two property. Okay, two property. Which one? First one, that sigma works as identity. Okay, on the field F. This sigma works as an identity on this field F. Okay, and second one, sigma works as G on yes. Okay, that is on S. This sigma is equal to what? This G is equal to sigma on this set yes. Is it correct? Okay, एखाद्या साठी परम्युटेशन एखाद्या परम्युटेशन साठी G एक्झिस्ट व्हायचं असेल. Okay, so that psi of sigma is equal to G. म्हणजे हा sigma कसा वर्क व्हायला पाहिजे? Sigma works as an identity on the field F, and sigma works as a G on set yes. Okay, so therefore, with the help of these two functions, which one? G and sigma. Okay, with these two functions, identity on F, capital F, and G on yes can be constructed. Sigma on capital K. Okay, because why? Because every element in capital K is obtainable as a result of the a result of finite number of operation. Which operation? Addition, subtraction, multiplication, and division. Okay, on elements of capital F and on alpha 1, alpha 2, so on, alpha m. Okay, we know that this one. Every element of K we can obtain by elements of F and alpha 1 up to so on, alpha m, because K is a splitting field of F of X. That is K is equal to F of alpha 1, alpha 2 up to so on, alpha m. Now, so this implies sigma image of every element of K can be constructed. Is it correct? Okay, sigma image of every element of K can be constructed
Yes,
with the
sir.
help of these two functions. With the help of these two functions. Okay, now say if suppose this A belongs to capital K. What is A? A can be obtainable with the help of alphas and wait a minute. This A can be written as alpha 1 K1, okay, plus alpha 2 K2 plus up to so on what? Alpha m Kn, where alpha 2 are the element of S and K1 K2 are the elements of the field F. Okay, every element of K we can obtain. So here apply this sigma on this element now. That is sigma of A is equal to sigma of alpha 1 K1 up to so on alpha m Km, where these alpha i's are belongs to S and K i's belongs to capital F, which is equal to this is sigma of alpha 1 into sigma of K1 plus up to so on sigma of alpha m into sigma of Km. Okay, now these are the elements of what? Yes, now alpha. Now sigma is equivalent to what? G. Okay, S वर कसा exist होईल हा कसा map होईल as G. Okay, so this is G of alpha 1. Sigma of alpha, sigma of K1. K1 is the element from F. Now sigma what I said leaves every element of F is fixed. That is identity functions of the guide. So this is K1 up to so on. This is G of alpha m, and this one is Km. Okay, so this is what sigma of A. So every element A belongs to K, we can define sigma such that. Okay, G of alpha 1 into K1, G of alpha 2 into K2 up to so on, G of alpha m into Km. So this implies sigma is determined completely. Okay, म्हणजे एखाद्या जी साठी आपल्याला काय मिळेल एखादा एक सिग्मा असा मिळेल जो S वर काय होईल इक्विव्हॅलेंट असेल. S is equal to G, completely determined completely. Okay, and will be extension of G, and this sigma या S वर काय होईल तुमचा G is equal to sigma, and this sigma is extension of this G on whole field K. Is it correct? This is determined completely.
Yes, sir. Sir, एकीला join होता येत नाही.
So sigma will be extension of G. Okay, so this implies G is what? Restriction of sigma. So that implies psi of sigma is equal to G. Okay, in the continuous we can define any permutation. For any permutation belongs to G, we can define one sigma belongs to GKF. Hence, this I is on true. Now, any doubt? Okay.
No,
So,
sir.
hence, GKF is what? Isomorphic to set of permutation, group of permutation. Sorry. Okay, the Galois group of a polynomial over the field F of characteristic 0 is isomorphic to group of permutation of its roots. Okay, now the next theorem is there. हा theorem सुद्धा खूप मोठा आहे, 2 लेक्चर लागतील. आज अर्ध होईल आणि उद्या अर्ध होईल. ओके, fundamental theorem of Galois theory. What is the name? Most important theorem. Fundamental theorem of Galois theory. Okay, look at the theorem. Fundamental theorem. Let capital K be a normal extension of a field F. Be a normal extension of a field capital F of characteristic 0. Then prove that. Then prove that there is a 1-1-1-1 correspondence. 1-1 correspondence between 1-to-1 correspondence between the set of subfield of capital K, which contains F, and the set of subgroup of GKF. Okay, what we have to show that there is a 1-to-1 correspondence. What is the meaning of 1-to-1 correspondence? 1-1 and on-to mapping. Okay. Okay.
1-1
There
and
is
on
a
to mapping.
mapping. There exists a mapping between the set of subfield of K, which contains F, and the set of subgroups of GKF. Okay. And further, if capital T is any subfield, capital T is the any subfield of capital K, okay, which contain capital F, then prove that. First one, dimension of K over T, dimension of K over T is equal to order of GKT. Okay, and dimension of T over F, that is degree of T over F, is equal to index of GKT. in GKF. Okay, माहिती आहे ना इंडेक्स म्हणजे काय? Index of H in G. That is order of G divided by order of H. Okay.
Yes, sir.
First, the dimension of degree of K over T is equal to order of GKT, and degree of T over F is what? Index of GKT in GKF. This is the first statement. Now, second one. If T is normal extension, T is what? Normal extension of capital F. If and only if this GKT is normal subgroup of GKT is normal subgroup of GKF. Now, third one, if capital T is normal extension of capital F, then GTF is isomorphic. Is isomorphic to GKF divided by quotient group. Okay, GKF divided by GKT. Okay, F is contained in T is contained in T. किती proof करायचं आपल्याला? पहा. Prove that there is a one-to-one correspondence. This is one first one. Then further prove that this is second thing. This is third thing. 3. This is fourth. And 5. If and only if okay, 5. And this one is 6. And it's 6 step ahead. Okay. Look at the statements once again. This is the only statement of the theorem. Let K be the normal extension of field F with characteristic 0. Then we have to prove that there is one-to-one correspondence between the set of subfield of K and F and the set of subgroups of GK. एक करत जाऊया. Okay, first we have to prove that there is a one-to-one correspondence between set of subfield of K which contain F and the set of subgroup of GK. कसा आहे तुमचा हा? This is F. Okay, K is the normal extension of F. Okay, now what is GKF? GKF is the set of those automorphisms of K which means every element of F is fixed. Okay, now we have to show that one-one correspondence between set of subfield of K. K चे असे subfield घ्यायचे. Suppose this is H. Is the subfield, not H. F1 here. Okay, wait. Suppose this is field F1 which contain F. This is F2. Okay, this is F3. Okay, F1, F2, F3. Okay, so here if the set X is the what? F1, F2, F3, F2, so on. Okay, so what is set X? Set X is nothing but set of subfields of capital K which contain what? Contains F. Okay, and what is Y? Y is set of, okay, GKF is what? Group, na? So here set of subgroup of GKF. Okay, suppose this is GKF. Okay, now this is set H which contains sigma 1, sigma 2, sigma 3 up to so on. Okay, we don't know how many elements are there. And here what H is the subgroup of GKF. Suppose this is H1, this is H1, H2 with the subgroup of all the subgroup of this is H2, this is a subgroup of GK. So Y contain what? H1, H2 up to so on. Okay. Finite is still infinite, like I don't know. Now we have to show that there exists a mapping between this set X and Y, which is 1, 1 on 2. Okay, so there exists a mapping in between X, Y, and Y such that that mapping is 1, 1 and on 2. Okay, this is the first thing. Any doubt in the first part? Okay, now proof.
No, sir.
Write down all the given things first. Let capital K be the normal extension of f of characteristic 0. Okay, now for any subfield T of K, for any subfield capital T of capital K which contain capital F, let this GKF, what is GKF? Sorry, what is GKT? What is GKT? Be the group of all automorphisms, all automorphisms of capital K which leaves every element of F is fixed, T is fixed, every element of T fixed. Okay, so now we have, look at here, sigma belongs to GKT. What it implies? Sigma leaves every element of capital T is what? Fixed. Okay. But F is contained in what? T na? Which is contained in K. And sigma leaves every element of T is fixed. So that means sigma leaves every element of capital F fixed. Is it correct? Why? Because F is contained in T.
Yes, sir.
Okay, so this implies this sigma belongs to G, K, Z. Okay, so this implies GKT is subset of what? G, K, F. Okay, any doubt up here? No.
No, sir.
Since both GKT and GKF are what subgroups? Subgroup of group of all automorphism of K. Okay, that is A of K. Na? These are the subgroups of these two one. Okay, and GKT is contained in GKF. These two are subgroups of these two. This one A of K. So this implies GKT is subgroup of GKF. Is it correct statement? करेक्ट आहे का नाही मला डाऊट आहे पण तरी चेक करा.
Yes, sir.
याचा नेमका अर्थ काय? सपोज G is the group. If A is subgroup of G, B is subgroup of G, and A is contained in B, then A is subgroup of B. याचा अर्थ असा झाला. Is it correct? करेक्ट आहे का हे? हे मला नक्की माहिती नाही, रिझल्ट माहिती नाही, कदाचित पहा या सिस्टम मध्ये असेल कदाचित मॉडेल अल्जेब्रा. हे चेक करून सांगा मला. तुम्ही चेक करा, मी चेक करा. If A is subgroup of G, पहा
Sir, repeat कर.
पहा. GK is subset of GKF. GKF is the subgroup of AK. Okay, and GKT is what? Also subgroup of AK. Is it correct? हा काय तुमचा T's element fix करतोय, हा F's element fix करतोय. This is the subgroup of AK. This one is subgroup of again AK. But GKT is contained in GKF. That means काय म्हणतोय both GKT and GKF are the subgroup of AK. Then GKT is subgroup of GKF. Is it correct? त्याचा अर्थ काय? If G A is subgroup of G, B is subgroup of G, and A is contained in B, that means A is the subgroup of B. असा झाला ना? चेक करा. मी ही चेक करेन, तुम्ही चेक करा. ओके.
येस सर.
आता हे स्टेटमेंट प्रूफ मध्ये तर दिलंय, म्हणजे असेलच ते GKT इज सबग्रुप. ओके, सबग्रुप ऑफ GKF. ओके, जर ग्रुप नसेल तर हा नॉर्मल होणारच नाही. तर बघा की GKT जर कोणाला क्वेश्चन ग्रुप काढायचा असेल तर हा काय असायला हवा? नॉर्मल सबग्रुप असायला. नॉर्मल सबग्रुप म्हणजे सबग्रुप असायलाच हवा, म्हणजे असणारच आहे तो, पण रिझल्ट मला माहित नाही. ओके, तो चेक करा तेवढं, मी हे चेक करेन बरं का. सो हियर द GKT इज द सबग्रुप ऑफ GKF. Okay, thus for any subfield capital T of capital K. Okay, thus for any subfield capital T of capital K which contains F, which contains capital F, we have found a subgroup. We have found a subgroup GKT of GKF. Okay, so here we found a subgroup GKT of what? GKF. Okay, now step number 1. We have to show that there is a mapping psi in between X and Y. What is X? Capital X, set of all the subfields of K which contain F. And what is Y? Set of subgroups of GKF. Okay, now step number 1.
सर ते स्टेटमेंट ट्रू असणारच आहे ना सबग्रुपचं.
There is a 1-1 correspondence between. हेच म्हणजे असणारच आहे, फक्त रिझल्ट मला माहिती नाही कुठल्या पेजला आहे, कुठल्या पेज नाही, तर ते पाहून त्याशिवाय नॉर्मल येणारच नाही ना. हा नॉर्मल ग्रुप आहे. आता क्वेश्चन ग्रुप फाइंड आउट केला म्हणजे हा नॉर्मल आहे ह्याच्यात. ओके नाही?
येस सर, तो एकेचा सबग्रुप आहे म्हटल्यानंतर त्याच्यात सगळ्या ग्रुपच्या प्रॉपर्टीज असणार, आणि जर GKF पण जर सबग्रुप असेल आणि जर कंटेंट असेल तर तो सबग्रुप असणारच. सबसेट आहे आणि तो एकेचा
असणारच आहे ना.
सबग्रुप आहे म्हटल्यावर
तेच
त्याचा
पण
सबग्रुप
मला रिझल्ट
असणार.
नक्की माहिती नव्हतं. हो.
येस सर.
Okay. Now, in step number 1, we have to prove that there is a 1-1 correspondence between the set of subfield of K which contain F and set of subgroup of GK. Okay. Now, step number 1, prove that there is 1-1 correspondence. 1-1 correspondence between set of subfield of capital K. Okay, set of subfield of capital K which contains F, which contains capital F, and set of subgroup of G, K, F. Okay, now write down. Let what is X? Set of subfield of capital K contains F. Okay, that is what? Suppose T. Okay, such that T is what? subfield of capital K and F is contained in T. And what is set Y? Y is equal to set of subgroup, set of subgroup of GKF. Okay, now define a mapping psi from X to Y such that psi of T. Okay, ह्याच्यामध्ये काय असतील सगळे फील्ड असतील तुमचे सब फील्ड असतील which contain it, that is T. ह्याच्यात काय असतील सगळे सेट ऑफ सबग्रुप ऑफ GKF. ओके, आता सबग्रुप कसे असतील H असेल GKT GKT and the mapping so I of T is equal to GKT. Okay, so the T1 असेल तर इथं GKT1, T2 असेल तर GKT2. Okay, for every subfield T of for every subfield capital T of capital K which contain F. Okay, now before going to prove the one-oneness, first we have to prove the ontoness. We have to prove that psi is onto. Okay, to prove that. This is step number 1, part 1. For any subgroup H, any subgroup H of GKF, let this KH, what is KH? Denotes the fixed field of H. Denote the fixed field of H. Set of those H is what? Fixed field of H. समजा या sigma H मध्ये sigma 1 जर असेल, okay, that sigma 1 leaves every element of H is fixed. Okay, so this is KH denote the fixed field of capital H. That is the set KH कसा असेल माझा? X belongs to K such that sigma of X is equal to X for all sigma belongs to H. Is it correct? Okay, so then if H is the subgroup of GKF, that means H contains automorphisms of K. Okay, so this H is what? Subfield of KH. KH is the denote subfield, fixed field of H. Okay, the fixed field of H means KH is equal to, take the elements from the field K, which leaves every element X fixed for all sigma belongs to H. Okay, so then KH is what? Is a subfield. The subfield of capital K containing F. Okay, that means highest काय होईल तुमचा? Since H is contained in what? GKF. Okay, सांगितलं. Wait a minute, कसं होईल तुम्हाला कळेल. This is what? GKF. And this one is? This is F. This one is K. Now this one is what? H. Suppose this is sigma 1, this is sigma 2. These are the elements of GK. Now this sigma 1 and sigma 2 leaves every element of F is fixed. Okay, H हा काय झाला? H is the subset of what? GK. Okay, that means H contains less element than GK. Less than or equal to. Okay, now suppose this H contains only sigma 2. आता कंडिशन कमी झाली तुमच्या इथे सिग्मा 1 आणि सिग्मा 2 दोन्हीला सॅटिस्फाय करायला हवी ही प्रॉपर्टी. ओके, now here H contain only sigma 2. So now fixed field of this H must be bigger than what? F. Is it correct? Okay, so here the KH
Yes, sir.
contains always F. So okay, so then KH is the subfield of K containing F. Okay, wait. Now, now we have to show that the ontologist now. So we have by the definition of psi of KH. Okay, apply on the field KH, which is equal to what? G K KH. Okay, by definition of psi. But in the last term, the last lectures, previous lecture, we proved that psi of KH. What is this one? H is equal to GKKH. Page number 977. पहा तुमच्या नोट्स मध्ये दिलेलं आहे. चॅप्टर नंबर युनिट नंबर 3 मध्ये. ओके, पेज नंबर 77 मध्ये आहे. Okay, GKKH is equal to H. We proved in the previous lecture. Okay, what is H? GKKH, that is nothing but H is equal to GKKH. Okay, so thus for any subgroup H of GKF. Okay, so this is the subgroup of what? GKF. Okay, so thus for any subgroup H of GKF, we have a subfield, KH of capital K containing capital F, such that psi of KH is equal to H, hence psi is on it. Is it correct? Okay, हे last term prove केले पहा.
Yes, sir.
Okay, hang with GKH is equal to H. Page number 77. मॅडमच्या जे आता नोट्स पाठवले तुम्हाला टेक्स्टबुकच्या त्याच्यावर पेजेस ते नंबर दिले. पेज नंबर 77 वर आहे. If KH is the fixed field of H, then H is equal to what? GKH. Set of those automorphisms of K which gives every element of KH is fixed. What is KH? KH is the subfield of H. Okay, so hence here psi is onto. Any doubt up to here? Okay, now we have to prove that
No,
psi
sir.
is 1, 1. Second, to prove that psi is 1, 1. Okay, since capital K is normal extension of capital F of characteristic 0, therefore this capital K is what? Splitting field. Splitting field of some polynomial of f of x belongs to f of x. Okay, this theorem also we proved in the previous lecture. Now, if the T is a subfield, if this T is the subfield of K which contains f, if this T is subfield of capital K which contains capital F, then this capital K is also Splitting field. Splitting field of f of x. Okay, f of x with the polynomial belongs to capital of x, but this f is contained in what? T. Okay, T is the subfield of K which contains na. So this f of x regarded
T.
as the polynomial over T. Okay, regarded as a polynomial over capital T. Okay, so hence, right, previous theorem. Okay, this is the reason for this step. Okay, now hence K is the normal extension of S. Why? K capital T is happens to this one is K, this one is T, this one is F. Okay, now K is what? Normal extension of capital T. By this theorem. Wait. Now T is the subfield of K which contains F now. So here K is the splitting field of f of x belongs to now T of x. Okay, hence f of x belongs to T of x. That means now this K is the normal extension of T. Okay, hence, hence, by the definition of normal extension, by the definition of normal extension, the fixed field of GKT is this T. Okay, that is K. Okay, this is suffix GKT, fixed field of GKT. Okay, this is the meaning of fixed field of GKT is equal to what? T. Okay, any doubt up to here? Okay, we take care of
No,
if
sir.
K is the splitting field. K is the normal extension of F with characteristic 0. Therefore, K will be the splitting field of some polynomial f of x belongs to capital of x. Now, this f of x belongs to now capital T of x. Okay, hence this K is the normal extension of now T. Now, if K is the normal extension of T, that means fixed field of GKT is T. That is K suffix GKT. That means GKT, the fixed field of GKT is equal to T. Now, take T1 and T2 with any two subfield of K which contains F. Let capital T1 and capital T2 be any two subfield of capital K which contains F, which contains capital F. Okay, now by this theorem again, by above step, K is what? Normal extension of T1 and T2. Okay, is it correct? Okay, f of x of polynomial belongs to f of x. That means
Yes,
f of
sir.
x belongs to T1 of x. F of x also belongs to T2 of x. Why? Because T1 and T2 contains this f. Okay, now consider the image of T1 and T2 are equal. By the definition of psi, this is G K T1. This is G K T2. Okay, by definition of psi, this implies GKT1 is equal to GKT2. This means fixed field of GKT1 is equal to what? fixed field of GK2. ओके, हे दोन्ही जर इक्वल असतील ह्या सेट मध्ये, यांची ऑर्डर पण कशी असेल, सेम असेल. This sigma belongs to this one GKT1, that sigma also belongs to what, GKT2. Okay, that implies the fixed field of GKT1 is equal to fixed field of GKT2. Now, by the above step, what is the fixed field of GKT1? K to the suffix
T1.
GKT1. Okay, which is equal to K to the suffix K GKT2. But this is what, T1. This one is T2. And psi is what? 1, 1.
1, 1.
Okay. So thus the defined mapping psi is 1, 1 and onto. Therefore, there exists a 1, 1 correspondence between the set of subfield of K containing F. Okay. So thus psi from X to Y is defined as above. As above is 1, 1 and onto. Okay. Thus there exists a 1, 1 correspondence. 1, 1 correspondence between the set of subfield of K, capital K, okay, containing F and set of subgroup of G, K, F. Okay, any doubt up here? Okay, now step number 2.
No, sir.
To prove that, look at here, step number 2. Theorem पहा. Dimension of K over T, okay, is equal to order of GKT, and dimension of T over F is equal to index of GKT in GKF. Okay, that is order of GKF upon order of GKT. Now, to prove that dimension of K over T is equal to order of GKT, and the dimension of T over F is equal to index of GKT in GKF. Okay, गोल तो सेंटर डायग्राम काढायचे. हा तुमचा T. This is T. This one is F. Okay, order of dimension of K over T. K over T is equal to order of GKT, and order of T over F is index of GKT in GKF. Now, as capital T is a subfield, it's a subfield of capital K containing F, capital F. Okay, it follows that K is what? In the above step, we proved K is normal extension of T. Okay, K is normal extension of T. Okay, and by the corollary, page number 79. Okay, by the previous lecture. Hmm. The degree of K over T is equal to order of GKT.
Order of GKT.
Okay, now as also capital K is normal extension of field F. Okay, of characteristic 0. We have by corollary again. Hmm. Order of K over F, that is degree of dimension of K over F, is equal to order of GK F. Okay, now this implies what is that? This is the K over F na, by the transitivity of finite extension. Degree of K over F is equal to degree of K over T into degree of T over F. Okay, so this is K over F is equal to order of GK. This is K over T into T over F. That's T over F, which is equal to order of GKF, which is equal to what is K over T is order of GKT. So this is order of GKT into degree of T over F, which is equal to order of GK, sorry, order of GKF. Okay, that implies this is T over F, dimension of degree of T over F is equal to order of GKF divided by order of GKT. That is index of, that is equal to index of GKT in GKF. Is it correct? Any doubt up to here?
Yes, sir.
ओके, दिसायला फक्त नाव अवघड दिसतात. इंडेक्स ऑफ
No,
जी
sir.
के टी जी एफ असं दिसतात अवघड, पण ते अवघड नाही, सोपीच आहे. ओके, समजणं समजण्यासारखं काय आहे ह्याच्यात? काहीच नाही. ओके, अँड द second and third statement we will prove in the next lecture. Okay, for today it is sufficient. Okay, what is second statement? T is the normal extension of F if and only if order of GKT is the normal extension of. That means fixed field of GK is equal to GF is equal to F. Okay, yes, second. Any doubt up to here? इथपर्यंत काही कोणाला शंका
No, sir.
समजतंय? काय अडचण नाही? Okay,
No, sir.
wait a minute.